lecture. This is the third lecture in a series of lecture on revised simplex method. So in the first two lectures I have discussed or revised simplex method, the conventional simplex method. So in these lectures I'll be introducing you to revised simplex method. So if you have not seen my previous two lectures, please see those two videos before going on watching this video. And also those who will be watching this video, I will recommend before you see this video, please revise a little bit on matrix multiplication methods, because we will be extensively using matrix multiplication in this method. So let's start. We'll start with an example. Before I start, I want to point out the reason why revised simplex method is important. In conventional simplex method, which if you do by any kind of computing device, and the values of the variables in each iteration, a large number of values has to be stored if the problem is a large one, and that requires much more computation. So if you use revised simplex method, the computational time decreases and it becomes easy, particularly when you are solving a large linear programming problem. And also in revised simplex method, we use matrix for holding the values, and matrix manipulations are much more easy from computational point of view. So therefore, from computational point of view, revised simplex method is an extremely useful method. However, solving it by manually, particularly if the problem becomes large or the number of constants become more, then it becomes difficult. However, we will be learning the method, that is the revised simplex method, by some simple problems, particularly two constraint equations and maximization problem only. That will be doing. So we'll start with example 1, where we maximize a function of z equal to 6x1 plus 5x2, which is an objective function subject to two constraints, x1 plus x2 less than equal to 5 and 3x1 plus 2x2 less than equal to 12, and x1 and x2 greater than equal to 0. So we'll write the canonical form of this equation. So this is the canonical form of this equation. So we have introduced two slack variables x3 and x4, and x1, x2, x3, x4 are greater than or equal to 0. Okay, so this will be solving by revised simplex method. Now, before we solve by revised simplex method, we will solve this by conventional method, and while solving by revised simplex method, I will correlate both this method so that you get a clear concept of the conventional method and the revised simplex method. So first we'll solve it by conventional method. So this is the solution of the conventional method. Sorry. Okay. So if you are watching this video, I want to take a picture of this slide and keep it in front of you while we'll be solving it by revised simplex method. Now here I want to point out some important points here. Notice that in all the three tables, the aij's of the basic variables are identity matrix, and cj minus zj of the basic variables are zeros rather. So here in the first table, my basic variables are x3 and x4. So here we have the identity matrix 1 0 0 1, and cj minus zj is 0 0. So this are my two statements. So the basic variables x3 and x1 here, so x3 is equal to 1 0 and x1 is equal to 0 1, again an identity matrix. The aij's of these two variables will form an identity matrix, and here you know c3 minus z3 is equal to 0 and c1 minus z1 equal to 0. And again in this table, this is x2 and x1 are the basic variables. So x2 is 1 0, x1 is 0 1, again an identity matrix, and you can see c2 minus z2 is equal to 0 and c1 minus z1 equal to 0. This is very important for you to understand. With this knowledge, we'll move on to revised simplex method. In revised simplex method, what we'll do is that we'll store the value in matrix form. Like here, P1 will represent a column matrix 1 3, P2 will represent a column matrix 1 2, P3 will represent a column matrix 1 0, P4 will represent a column matrix 0 1, and B matrix, which is a column matrix, will be the right hand side constraints 5 12. And we'll start with the equation. We'll start with the basic feasible solution. X3 is equal to 5 and x4 is equal to 12. That's we do in conventional method also. Here also we'll be doing the same thing. So take a picture of this and keep it in front of you while you watch the rest of the method. So here, so I have stored the values in column matrix. P1 is equal to 1 3, P2 is equal to like this, and we'll start with iteration 1. So in conventional method also we start with a basic feasible solution. Here also we'll start with the basic feasible solution where x1 x2 equal to 0 equal to z. So all x1 x2 equal to 0 and z will be equal to 0 if x1 x2 equal to 0, and x3 is equal to 5 and x4 is equal to 12. We'll start with that equation with this basic feasible solution. So here xb I have taken the x variables, the basic variables x3 x4 equal to 5 12, and the basic matrix consists of the column matrix of the basic variables in this manner. So p3 p4 it comes out to be 1 0. We all know that the basis matrix has to be 0, at least in the first case. The basis matrix will be an identity matrix. So this is 1 0 0 1, which is equal to identity matrix, and the transpose of this identity matrix will also be an identity matrix. So therefore B equal to B inverse. Okay, so now we have to find out, once we have found out B inverse, I have to find out Cj minus Zj. This B inverse is required to find out Cj minus Zj bar. So Cj minus Zj bar is equal to Cj minus summation of Cb Aij, which is basically equal to Cj minus Cb Pj bar. Now what is this Cb? Cb is a row matrix. I'll come to that. Cb is a row matrix. I'll come to Pj bar later. So first let me explain. Cb is a row matrix consisting of the values of the coefficient of the basic variables in the objective function. So here the basic variables are x3 and x4. So it will be a row matrix 0 0. So the coefficient of these variables x3 and x4 in the objective functions are 0 and 0 respectively. So Cb will be equal to a row matrix of 0 and 0. Now the question arises, why Cb will be a row matrix? Why every other matrix is a column matrix? Why Cb is a row matrix? Now Cb is a row matrix, it is by design. Then only we will be able to get the value of Cj minus Zj. That's why Cb is a row matrix. Now here Pj bar is equal to B inverse Pj. So in that manner we have defined. So it will be Cb B inverse Pj. Pj is what? Pj is the pivot column. So Cj minus Zj bar is equal to Cj minus y, where y is equal to Cb B inverse Pj. So Cb, I have already said, is the coefficient of the basic variables in the objective functions. In this case x3 and x4. So the coefficient of x3 and x4 in the objective functions are 0 0. So Cb is 0 0. So y in this case will be Cb B inverse. B inverse is an identity matrix. So therefore it will be equal to Cb equal to 0 0. Then we will find out C1 Z1 and C2 Z2, and we will not find out C3 Z3 bar and C4 Z4 bar because x3 and x4 are the basic variables. So we know beforehand only that C3 minus Z3 bar will be equal to 0 and C4 minus Z4 bar equal to 0 because these two are basic variables. So I am only interested in finding out Cj minus Zj bar of the non-basic variables. So in this case it comes out to be 6. C1 is 6, that is the coefficient of x1 in objective function. So 6 minus CB 0 0 into P1. P1 is 1 3. So 0 into 1 plus 0 into 3 is equal to 0. So that will give you 6. Similarly, this will give you 5. Now how to test whether this is an optimal solution or not? So out of these two calculations, both are positive. Since either one of them is positive, if any one of them is positive, then it is not an optimal solution. So definitely this is not an optimal solution, and the entering variable will be the one which is the highest. So here 6 is the highest, so P1 will be the pivot column and x1 will be the entering variable. I repeat, P1 will be the pivot column and x1 will be the entering variable. So here this will be x1 will be the entering variable and P1 will be the pivot column. So I know x1 is now becoming a basic variable. From non-basic it will become a basic variable. Now which basic variable will exit the basis? For that we have to find out the value of theta, like we have done in conventional method. To find out the value of theta, we require to find Pj bar, that is P1 bar. So P1 bar will be B inverse bar, and B inverse identity matrix, so it will be equal to P1. So P1 in this case is 1 by 3. So now here my initial solution was, if I remember it correctly, it was 5 and 12. x3 is equal to 5 and x4 is equal to 12. So now we have to find out this 5 minus 1 into theta greater than equal to 0 and 12 minus 3 into theta greater than equal to 0. Out of these two equations, whichever gives me the minimum value of theta will be the value of theta. So here theta is equal to 5 and theta is equal to 4. So the value of theta is 4. So in next iteration, xb will be equal to, see which one is entering. So here the exiting variable will be x4, and in place of x4 x1 will be entering, so it will be x3 and x1, and this is equal to 5 minus 1 into 4, and this is 4, so we have 1 4. Okay, so here to find out the minimum theta, 5 minus 1 into theta greater than equal to 0 and 12 minus 3 theta greater than equal to 0. So this gives theta is equal to 4, and from the next iteration, in the next iteration, xb will be equal to x3 x1. So we'll start this in the next iteration. Now this is my basic variable, x3 and x1 are my now current basic variables. So and we start with 5 minus theta, so it is 1 4. Now if we see if you look at the picture that you have taken of the of my conventional simplex solutions, you will find that x3 is equal to 1 in the second simplex table and x1 is equal to 4. So the basis matrix will be the column matrix of P3 and P1. So P3 is equal to 1 0 and P1 equal to 1 3. Now this is not an identity matrix, and B inverse of this will not be equal to B. So we have to find out the B inverse. Now we know a formula for finding out the B inverse of a 2 by 2 matrix, and we can do it easily. Otherwise, finding out transpose of or inverse of a matrix can be very cumbersome manually. Computationally it is very easy. So suppose 2 by 2 matrix B is equal to A B C D, then the inverse B inverse will be 1 by AD minus BC D. This will be interchanged and minus will be here, so minus B minus C, so it will be here. So in this case, if it is 1 0, so this will be equal to B inverse in this case will be equal to 1 by 1 into 3 minus 0 into 1, into it will be 3 and 1 minus 0 is 0 and this is minus 1. So which gives us, if you take the 1 by 3 inside, it will give us 1 minus 1 by 3, 0, 1 by 3 will be this. And again, if you see my conventional method slide solution, B inverse will be exactly equal to this. So here you can find out. So it comes out to be 1 minus 1 by 3, 0, 1 by 3. So if you look at this solution again of the conventional method, so here it becomes 1 minus 1 by 3, 0, 1 by 3, and my next solution is x3 is equal to 1 and x1 is equal to 4. So with this we move on. With this we move on to the next part of this, that is the next, yes, that is we'll find out y is equal to CB V inverse. Now what is my CB? Now CB are the row matrix consisting of the coefficient of the basic variables in the objective functions. Now what is my basic variable here? x3 and x1. So x3's coefficient in the basic objective function is 0 and the coefficient of x1 in the objective function is 6. So CB has to be 0, 6. Now I am interested in finding out y. Y is equal to CB V inverse equal to 0, 6, 1, 0 minus 1 by 3 . So this will give us 0 into 1 plus 0 into 6 is equal to 0, and 0 into minus 1 by 3 is equal to 0, plus 6 into 2 by 3 will be giving me 0, 2. Yes, so y comes out to be 0, 2. Y comes out to be 0, 2. Now I am interested in finding out the non-basic Cj minus Zj of the non-basic variable. So we'll find out C4 minus Z4. C4 minus Z4 is, this is C4, which is 0. The coefficient of x4 in the basic objective function is 0. So this minus 0 into 2 into 0 into 1. So 0 into 0 plus 2 into 1 will give you 2. So this is 1. This is 2 minus 2. Now you will understand why you have taken a row matrix, because if you multiply this one row matrix with a one column matrix, we get a one element here. So one element minus this will give me the value of Cj minus Zj. That's why we have taken it as a row matrix. Similarly, C2 minus Z2 can be found out. It comes up to 1. Now since this is 1, this is not optimal. Solution is not optimal. And therefore this will be the entering variable, and for finding out the exiting variable I have to find out P2 bar. P2 bar is equal to B inverse P2. So B inverse P2 is this. So 1 okay, so here 1 into minus 1 by 3 here into this will give you 1 into 1 plus minus 2 by 1 by 3. So 1 minus 2 by 3 will give you 1 by 3, and 0 into 1 plus 2 by 3 will give you 2 by 3. So P2 we have this, and initial my solution was 1 and 4. So 1 minus initial solution means x3 was 1 and x4 was x1 was 4. So this minus 1/3 of theta and this minus 2/3 of theta this is greater than equal to 0. So we'll take either of this one, which will give minimum theta. So minimum theta comes out to be here 3. So it is from this equation. So x3 will be the exiting variables and p3 will be the pivot column. Sorry, x3 will be the exiting variable. So we move on to the next iteration. In next iteration, we have xb is equal to this. This theta we already found out theta. So from the second equation we can find, putting the value of theta in the second equation in the earlier iteration. So we can find out this is equal to 2. So 3, 2. So now we start with x2 is equal to 3 and x1 is equal to 2. Now we have to check whether this is an optimal solution or not. To check this whether this is an optimal solution or not, we have to find out the Cj minus Zj bar. So to find out that, we require to find out B and B inverse and Y and Cb. Now Cb is now consisting of this x2, the coefficient of x2 in the equation is I think 5 and this is 6. So Cb will be 5, 6. So now before we move on to that, now B becomes equal to P2, P1. So it will be 1 by 2, 1 by 3. So if this is 1 by 2, 1 by 3, so B inverse will be equal to 3 minus 1 into 3 minus 1 into 2 will be 3 minus 1 minus 2, 1, which gives us 3 minus 1 minus 2, 1. So this is what we get. Again we will check the conventional solution. Okay, so here you can see, so this value is the B inverse in the third iteration. That is exactly what we are getting, and this is what we got at the start of the third iteration. X2 is equal to 3 and x1 is equal to 2. So you can see the both are actually matching. Only thing is that we are doing it in a different manner, and we will see that we will be getting minus 3, C3 minus Z3 as minus 3 and C4 minus Z4 as minus 1, and therefore this will be the optimal solution that we'll check. So we are here. So here, so Cb is equal to 5, 6 as we have found out here, and Y will be equal to 5 into 3 plus 2 minus 2 into 6, it will give it 12. So 15 minus 12 is 3, and 5 into minus 1 plus 6 into 1 will give you 1. So Y becomes equal to be 3, 1. So once we have this, we will find out C3 minus Z3, which comes out to be minus 3 as we have seen in the conventional method, and C4 minus Z4 is equal to minus 1, same as we have found out in the conventional method, and we know C2 minus Z2 will be equal to 0, and C1 minus Z1 bar will also be equal to 0, because those are basic variables in this particular step. So this is an optimal solution. Both the values are negative, less than 0, so it is an optimal solution. And in this solution we have started with x3 is equal to 2, 3 and x1 is equal to 2. So this is my solution of the problem, and the optimum value will be 6 into 2 plus 5 into 3, it will be 27. So this is the solution. So I hope this method is clear to you by now. We'll solve one more problem in the next lecture, and if you watch that video, I think your concept of revised simplex method will be very, very clear. So I thank you for watching this video.